the one electron Fock equation is formulated for molecular orbital as function of position, right? For a continuous, for this clouds, bubbles that we were drawing in the labs, right? Okay. And on one hand. On another hand, we did agree that molecular orbitals are represented as linear combination, expansion coefficients between atomic and molecular orbitals. So the only practical task that I want to complete today is to convert one electronic mean field equation into the language from the language of differential equations into language of linear algebra, into language of matrices, into language for discrete expansion coefficients. Whew. Basically, I'm done. The rest are technical details. Maybe let's practice a little discussion. I don't know if it is really good, but I like it much. Can you share your vision of our plan for today? And you need to unmute the microphones. I think they're muted. Can you try say something? Kia?
Yeah.
Okay. Yeah, good. It works. It works. So, can you try summarizing what is our plan? Do not worry. Just to best of your understanding. And for me, it will be. I will check if I'm able to speak comprehensively. That you understand.
The continuation of the last class. So today you will explain more about the Hartree fork and what we did in the last lab session. So you want to explain those last lab session. You just showed us that how to use the software. In today's lecture, you want to explain those things in theoretical way.
Okay. Nothing is wrong, but it is very general. Let's be more specific. So, Lola, please try just share your vision of the plans for today.
Okay. From what I understand, today you're going to be sharing the practical concepts of the theories that we learned in the previous class about direct, Coulomb, and exchange. I'm probably going to have to modify some Hartree fork. I really don't know, but it's basically practical concepts in terms of what programs to use and what equations. Yeah.
Okay. Yeah. Thank you. Everything is correct, but I'm looking for more detailization. Let's try. Steven, would you like to try sharing your vision of the plans for today?
So I would think that today we'd be I would understand that today we are going to be covering how one gets from sort of an initial suggestion of an equation into a final result.
Mm-hmm.
And I'm going to cheat a bit. I'm going to look a bit at the PowerPoint that you sent us.
Sure. It's legitimate.
So basically, you want to explain today Hartree-Fock equation and DFT. I think.
No. DFT will be another month.
Okay,
Uh,
another.
yeah, it is. DFT is easier than Hartree-Fock, but we need another month to learn it. Only Hartree-Fock today.
So only Hartree-Fock, yeah. It's written in your slide, Hartree-Fock equation, Hartree-Fock equation.
Yeah. So Steven, what your cheating gives us?
Yes. So today we'll be going over, we should be going over the various steps of the Hartree-Fock method and how that can achieve us in a result of computing the orbitals of a molecule.
Okay. I'm happy. Everything is correct, but there is a room for a few bit details. So, Sarah, would you like to try?
As other students mentioned, I think we are going to continue about the Hartree-Fock and the materials that we had in the previous lab, maybe more theoretically, and the concepts of them. Maybe you are going to mention them in today's lecture.
Okay. Yeah, that's correct. And do you think that something compared to what I was telling and what everyone tries to understand, there are few technical details I'm missing? Just try to guess what is missing.
You were just explaining the electrons. I'm not sure.
Okay. Yeah, but thank you. You did everything correct. I'll keep the intrigue. Let Boston try, and then I give the full answer as I see.
I have nothing more to add than what everyone else has already said.
No,
Sorry.
You can. Please try. I hope everyone did perfectly and answered correctly. I just would like to hear a few more details. And now I give a bad grade to myself that I didn't communicate the essence.
I've got nothing more to add other than looking more into Hartree-Fock and perhaps the applications of it, or how it's applied. I mean,
between theory and applications, there are implementations. There are ways how equations are programmed into computer, right? And equations are not programming cannot be done or very uncomfortable to do for continuous function. All actual programming is done in matrix form for discrete elements. So we are going to convert general theoretical Hartree-Fock equations into equations for matrix elements, for expansion coefficient. So we will be doing Hartree-Fock equations for molecular orbital expansion coefficient, letter C. So we will get some matrix equation, and then we'll get an algorithm that allows us to solve this equation. So I'm happy with everyone answering. I'm no problems. I'm just trying to bring it. Two keywords: matrix and algorithm.
Matrix
and algorithm. Okay, and matrix we'll just understand it through slides, and algorithm we will practice to reconstruct this algorithm together as a quiz in like half an hour. Whew. Okay, I'm going to start sharing screen. So here are the things that we did last time, right? You remember? I remember Kay was asking questions about this black box that sounded as something intuitive to me, but Kay told that no, it should be explained as equation. So one electron is getting repelled from another electron, which is in a black box in the unknown structure that we integrated out. And the same for exchange. And if we do know this one electron operators, J and K, if we do know kinetic energy for one electron and one electron attracting to all ions, then we do have Fock operator, which is the heart of Hartree Fock. So this equation, this operator, is a replacement of Hamiltonian. So one needs to plug it into Schrödinger equation.
Sorry, which one the replacement of
Schrödinger. Hamiltonian, yes. F is instead of H.
Okay.
So we are looking for eigenstates of this Fock operator. We are looking for this phi, which is molecular orbital, one electron molecular orbital. And this phi, I apologize for a little scratchy notes. I promise to myself improve them from year to year. So this phi depends on r, of position of one electron in space, which is correct, but computationally not efficient. So the goal for next about 20 minutes, my goal is to convert this equation from differential continuous form into matrix form. And then we'll do algorithm. So two things for today, matrix and algorithm. So on this way, I want to introduce another concept related to basis functions, atomic basis functions, that were introduced a week ago by Lina and Kaya. So atomic orbitals, basis functions.
Okay. We showed those things last week.
Yes. So atomic orbitals are centered on atoms, right? And there are several atoms, several ions in the model. So if we consider atomic orbitals localized on one atom, then they all are orthogonal. Then if one takes atomic orbital and multiply it by another atomic orbital and integrate, one will get either 0 or 1. 1 if it is the same, 0 if they are different. Correct? But situation is getting different if atomic orbitals are localized on different atoms. So for same, it is already written. For the same, it will be chi mu star chi mu d r will be equal either 0 or 1 if it is same ion.
Yeah.
Right? But if the atomic orbitals are localized on different ions, for example, if it is s orbital on ion number 1 and p orbital on ion number 2, and then we'll try to perform this operation. Take basis function, s function on one ion, p function on the other. The result of their convolution, of their integration, multiplication and integration, will be neither 0 nor 1. Right? Because hydrogen-like atomic orbitals are orthogonal only in the frame of one ion, one atom. But if there are several ions, then there is no theorems telling that they should be orthogonal. You see? And it makes, I wouldn't say big discomfort, but it adds specific for describing molecules on quantum level. So if it is the same ion, then we call it will be delta function, delta mu nu, which is either 0 or 1. But if it is different ions, we need a special symbol just to speak about it. We need to name this degree of overlap. And we can assign a letter S and call that letter S stands for overlap matrix element, for degree of coincidence or not coincidence of orbitals in general, whether they are on the same ion or different ion. So if they overlap a lot, then it will be either 0 or 1. If they overlap in a tiny area, then it will be a number between 0 and 1, something like 0.01 or whatever.
In your slide, Professor, you wrote R1, R1, psi, mu, bracket R1, then psi, that viscosity sign, I guess, the V sign, then R1. So then again, you change it
Yes,
R1 and to
yes.
R2. So which one?
No. I apologize for a little ugly writing, but it is correct. I can defend it.
Okay.
So for lowercase r, which is position of electron, it is the same electron, lowercase r1, because molecular orbital is for one electron.
Okay.
And uppercase r is for different ions. For example, ion number 1 and ion number 2. So here we integrate over position of one electron, but positions of the ions are parameters of this matrix element. And to be very, very mathematically meticulous, one needs to put 4 indices: mu, and here should be R capital 1, R capital 2, to specify between which ions. Make sense? So if we would perform our consideration in the orthogonal basis, then there are some standard procedures based on the orthogonality. But now our basis is not orthogonal, and we need some specifics. Okay, next point. We already covered it. So for mathematical comfort, one avoids to recomputing Coulomb and exchange matrix elements for molecular orbitals again and again. Instead, one finds Coulomb and exchange matrix elements in the basis of atomic orbitals and then use them as a building blocks multiplied by expansion coefficients when they are known. So now my conscience is clear. I delivered it, but this concept is technical. If you do not feel comfortable, it's not a big loss. Although I would be happy to go over it. So we will waste time. I see from your faces that you probably want more. I have another slide later. Let me just tell that matrix elements are computed in for atomic orbitals, and then later on forwarded into basis of molecular orbitals. Okay. So we do need to solve this one electron. We need to convert this one electron Fock equation into basis of atomic orbitals. And here is the main technical slide for today. There will be something more important as an outcome, as a result, but in terms of procedure, here is the main slide. So if you elect to follow the story of the lecture, this is one of the focal points to focus and think about it. So the equation in the first line is differential orbital for continuous. So it is continuous wave function. T U O is molecular orbital. So it is basically the stuff that we draw in Gauss view. And here is the expansion coefficient. So molecular orbital is represented as summation of multiple atomic orbitals with set of unknown expansion coefficients. Expansion coefficient. So we are going to plug in this expression for phi in every times we see symbol phi in the first line. So we will plug second line into the first line and process in a standard way. And look what happens with it. As a result, I'm playing open cards. As a result, we are going to get an equation for this expansion coefficient. We will do some tricks to get rid of atomic orbitals. We already are getting rid of molecular orbitals by plugging it in, and there will be equation for expansion coefficient, which is actually solved by the software, which is programmed in the computer code. Okay. So how do we practice it? I have about 20 slides which repeat again and again the same idea, and I have problem to select which one is better. But from now on, I'm going to share the same information just from different points of view. So here is in black color is the equation from previous slide. So we do have Fock operator and unknown energy. And then we plug in expression for molecular orbital. Right? So molecular orbital is expressed as summation over atomic orbitals. So now the next step is to get rid of atomic orbitals. So in order to get rid of atomic orbitals, typically I want to practice orthogonality, or the property which does replace orthogonality in this system. So in order to practice orthogonality, I do multiply left and right sides of this equation by atomic orbital of the independent index mu with star, and then perform integration over the position of electron. So we have the same electron here, there, and there. So why do I do it? Because upon taking integral over the variable R1, I will remove dependence on R1. I will remove atomic orbital here and there. And depending on the structure and properties of the Fock operator, this integration will give me matrix elements, which can be either zeros or ones or something more specific. So on the left and right, I will get only matrix elements. So we will convert from differential operator to some numbers. And since there are multiple indices and summations, likely these numbers will be arranged in same format as typically we do for matrices. So in the lower line, in the second line, I repeat the same idea, the same equation with slight rearrangement of terms. So I take summation and the expansion coefficient C to the front. Because coefficient C do not depend on the electronic position. And I also take it up front here. Then we do have summation, and after summation, let me use another highlight font, yellowish. We do have integration of Fock operator in basis of atomic orbitals, which is nothing but matrix element of Fock operator. And on the right side, we will have integration of product of the atomic orbital. So, a couple of slides ago, I saw question in your faces. When let me quickly scroll back. So I saw questions on your faces when I was showing this slide, and when I told that matrix elements are computed for atomic orbitals and then promoted to molecular orbitals. Right now, let's go back to this slide. So you see this yellowish highlights.
Yeah.
So they deal with atomic orbitals only. They compute matrix elements in basis of atomic orbitals. So this F sub mu nu and S sub mu nu can be found once and forever for given molecule. We do not, even if we modify expansion coefficients C, and we need to recompute values of Coulomb and exchange between different molecular orbitals, the building blocks, the integrals, the matrix elements of the Fock operator in atomic basis can be computed before we start any practical calculation, and you can save time on this calculation. So the yellowish thing on the right is our overlap matrix element. If we would apply this theory for one atom only, then this S sub mu nu will convert into delta function. Will be either 0 or 1. In practical calculations for molecules, it can be anything between 0 and 1. Overlap of atomic orbitals. The thing on the left, matrix element of Fock operator, does include matrix element of kinetic energy, of attraction of electron to ions, repulsion of our selected electron from the rest electrons, and then exchange energy of attraction of our selected electron to others. Whew. Now there will be several slides which just repeat the same idea in maybe different fonts. So plugging in, integrating, defining the overlap matrix element, again multiplying left and right by atomic orbital and integrating. Here I found my own error, should be R1. Orbital. And here is the equation that just typed a little bit better, but it is the same thing that we just considered a minute ago. So matrix element of Fock operator in basis of atomic orbitals and overlapped matrix element. So now next little intellectual step. Matrix elements are numbers, right? They're not operators anymore. Yes? Matrix elements are numbers. It's not a question. I do not doubt that you agree with me. It is a rhetoric question. Rhetoric question. But let me attract your attention. This matrix element is computed for set of number of indices, mu and nu, right? So mu and nu are index, like I'm lazy and I'm not writing all details of the indices, but under index, for example, mu, I understand that it shows which ion it is. So ion number, let's say, and then it gives principal quantum number, orbital quantum number, magnetic quantum number, and spin quantum number. So it is all information. And since we have many atoms, many ions, and many quantum numbers for their set of atomic orbitals, it's basically all basis functions from your basis set, which is like a couple hundred, even for small molecules. And then we have about 100 values of mu index, 100 values for nu index, and then it is a matrix 100 by 100. So this F mu nu is a matrix, right? And this S mu nu is also a matrix. Yes, mu nu. So the summation in front of a matrix. Oh, yeah. One and another little thing. I always was planning to say, but let me focus your attention on it. Select some nice color. So there is index nu here and index nu there, and here and index nu there. So we do have an expression that reads the following way: summation mu f mu mu c mu, and the index I is the same for each element in this equation. We are not modifying it. So please tell me if this expression reminds you something from the linear algebra course. Boston, please try to answer this hard question. And do not hesitate, you can throw in some crazy ideas. So let me give a little hint. And anyone is welcome to speak. So we multiply two objects. One object has two indices, another object has one index. And we are making summation over indices here and there. Does it remind you something? It does. I'm trying to convince you. It does. Let me illustrate, and you will enjoy it. So let's. I have slides repeating it again and again, but if I try to write it alive with support discussion, it will be more interesting. Let's say we have F1 1, F1 2, F2 1, F2 2. Right? It is an object with two indices. Agree? First index is mu, second is nu. Then we have C1, C2. When we, so what do you do if you see such notation? Steven? What do you do if you see matrix times vector?
A matrix times a vector is.
Do not give the literal answer. Just tell which mathematical procedure you can do between matrix and vector. The mathematical procedure starts with letter M.
Oh, is it multiplying?
Yes. Yes. Perfectly.
Okay, I was thinking dot product.
No. Multiplication. And I have no doubt that you all can write the answer, right? So something like row by column rule. Row by column for the first element. So which will be F1 1 C1 plus F1 2 C2. Do I do any mistakes?
No.
Probably yes, but not on this slide. Now let me show you something that I have no doubts you are aware of it, but let me focus your attention. Let's look here. So second index 1 and of the matrix, and index of the vector is also 1, right? Now for the matrix, second index 2, and for vector, index is also 2, right? Now let's just summarize what was written here. So it is F1, and then we put, let's say, letter mu, C sub mu, summation over mu, right? So second index of matrix and index of vector do coincide, right? So expression with summation, 2 object index and 1 object index, corresponds to matrix by vector multiplication, right? Now let's look once again on the previous slide. So here we have two index matrix and a vector, and here again we have 2 index matrix and vector. So it is on the left and right side we have matrix by vector multiplication. Okay. So let's go forward to the slides, and so matrix by vector. F mu times C mu. S mu C mu equals summation. And you see that and the names for these objects are Fock matrix, because it is matrix of matrix elements of Fock operator. So Fock matrix and overlap matrix. and here is the shape. So Hartree and Fogg were not thinking this way because at their time there were no computers. There were only abacus, and they didn't care. But in 50s, some prototypical computers were designed, and there was another scientist, Clemens Ruthan, who converted Hartree-Fock equations into matrix form, and therefore in computation it is nowadays three names: Hartree-Fock, Ruthan. So today we followed, and there are some details of his biography related with his inspiration of from going to symphonical orchestra, and then after that deriving equations. So if you need to derive equation, you need to go and listen to symphony. It's a lesson from Dr. Ruthan. So his equation, and we can agree between us that this mathematical form is correct, but it doesn't click to our intuition. For some people, for majority of people, writing vectors is more reasonable in like as a column of numbers, right? And writing matrices is more natural as writing the square box of numbers. So we can convert this one electron equation for matrix element for expansion coefficient matrix elements in terms of molecular orbital vector. We can even put the symbol of vector here on Fock matrix and overlap matrix, and you can call use the fat symbol F for Fock, and thick symbol for fat, and then fat symbol S for overlap matrix. Okay, make sense? Whew. So we are going from Fock to Ruthan, right? And here how the equation looks like. So we multiply Fock matrix by vector of molecular orbital expansion coefficients, then S matrix by expansion coefficient, and we have unknown energy up front. And we can subtract left and right part, then elements will be Fock F minus S multiplied by C. F minus energy times S multiplied by C equals 0. So it's a standard eigen value problem that we do not need to solve it. There are computer programs developed again and again that solve it quite efficiently. And modern computers, there are linear algebra packages, LinPack, LaPack, and there is an advent of quantum computers that solve things parallel, that equations like that are solved naturally. It's standard problem that being solved by our human civilization. So one electron equation for Fock operator, or one can write to find eigenvalues, one needs to make determinant of this matrix equals 0, which gives if it will be a really small matrix, we can write the characteristic equation, find roots, and identify the eigenenergies. But for now, for us, it is done by computers. Okay, and we are approaching the end. So the thing is that if we solve it once, we can find the energy. After we find molecular orbitals, we can combine them back into Slater determinant and use the Slater determinant to find total energy. But this total energy, since we are solving one electron orbital, one electron equations instead of multi-electron, it will be not exact. So the goal is to use this expansion coefficient C to go in a feedback loop and redefine the background field of the rest of electrons. So the main assumption that some people are skipping at this point is that molecular orbitals that we find for one electron will be valid for all electrons. So there will be a set of molecular orbitals, and they will be occupied by all electrons according to Pauli principle, of our principle. And then one forms multi-electron system and finds total energy. And then this total energy is recorded. Then molecular orbitals are forwarded in a feedback, and then procedure is repeated until total energy is found again. And this computation of total energy is repeated again and again at step number J, until energy at step number J plus 1 minus energy at step minus J will become smaller than our precision requested tolerance limit. So in this sense, Hartree-Fock procedure is analogous to our procedure to optimize geometry. But instead of optimizing position in space, now we optimize expansion coefficient, this C capital things. So total energy can be computed this way. So energy of molecular orbitals plus pairwise interactions, Coulomb exchange. And a little technical detail that here are, that I underline, matrix element in atomic orbitals. And here this P lambda sigma is a combination of molecular expansion coefficient. So for understanding of theory, it is not important, but for notation of Gaussian software, it is how they program. So after they know molecular orbitals, they construct their product, they call it density matrix, and they multiply this product of molecular orbitals with Coulomb exchange matrix elements and put it into the Fock matrix. Just a little technical details if you are super curious. Now, we are going to try to fill the box. So let me invite you to follow the link for the quiz. And so please, yes. And oh, someone is already made the first step. I don't remember. I don't know. Who did it?
Me.
Who moved this symbol?
Me.
You? Okay, thank you, Kia. So
it will be the last one.
Yes, absolutely correct. So Kia did the easiest part, I would say. So let's try to take the remaining 1, 2, 3, 4 boxes and place these boxes into different sides of this flowchart. So who did this density matrix motion?
Me.
No, put it back. There are 4 other people who maybe okay, you already did your tolerance limit. Now there are only 4 boxes. So who is Lola? Please try to move one of the boxes somewhere.
Yeah, I'm trying. I'm trying to zoom in because I can't see it properly.
were you able to connect to this? And you just take something and move it, drag and drop, like take and move, take and move. So which box are you trying, Lola? Which box are you trying to move?
I'm trying to move the diagonalized fork, the second to the last one.
This one?
No, the
This
one before the
one,
last one.
diagonalized fork matrix.
Yeah.
Okay. Okay, and where you want to move it? To which box? Yes. I would say it is correct. So can you try to move it? If no, perfect. Yeah. So Lola is done. Now, Sarah, would you like to try move some boxes?
It was me actually. I moved the FC equal to.
Okay. Okay. But Lola already discussed it. So now you have chance to move one more box.
Okay.
So you can tell first what you plan to move.
I think the first one.
Okay. And where do you plan to move it?
It should go to the first one.
Yes. One? Yes. Correct. Please do. Okay. Thank you. Steven. Now you have 50% chance of success, even if you move them randomly. So which box are you planning to move? Okay.
I'm planning to move the form Fock matrix.
And where are you planning to move it?
To the box after prepare density matrix and before diagonalize Fock matrix.
Yes, excellent. Please do. Yes, thank you. Boston, you have 100% chance of success. Perfect, perfect. So, you see the challenge for the code, not for us as humans, but for the code, that after each time the coefficients C, expansion coefficients C are found, if the tolerance limit is not matched, then we form different density matrix. And the Fock matrix, although it is composed of the same atomic orbitals, it will have different values upon this recomputing of molecular orbitals. And then with this new Fock matrix, we rediagonalize, find total energy, and check whether it is matches criteria. In order to start this calculation, one of course needs to know positions of ions, and to practice this initial density matrix, one needs some initial guess of molecular orbitals, random numbers, or from lower level calculation, or some just assuming that, well, we will not discuss it right now, but the overall procedure in some sense similar to finding minimum on the potential energy surface. Many thanks for successful completion of the quiz. I think here is the answer, and we are successfully approached the planned end of the lecture.